Hello friends. So far I have spoken about expectation of simple random variable and non-negative, extended it to the concept of expectation of non-negative valued random variables, and we have stated and proved a number of properties of expectation of non-negative valued random variables, and two important lemmas have been stated. One important lemma and two important theorems have been stated. One is a monotone convergence theorem, another is Fatou's lemma. Another is the lemma that if you have a non-negative random variable, then you can construct a sequence of non-negative valued simple random variables which are non-decreasing and pointwise converge to the given random variable. Using that lemma and MCT, you get a second definition of expectation of a non-negative variable in the form of a limit, which we have discussed in the last lecture. Today I am proceeding towards the third stage of the theory of expectation, which is to define expectation of any real valued random variable. So here this equation is the first important concept to realize when you think of defining expectation of any real valued random variable. So to again brush up your memory, what is a real valued random variable? It is a mapping on a probability space. So the domain of this map X is the sample space, the set of all possible outcomes of the random experiments. We always do not write it, but please remember, whenever we are talking about a random variable, there is an underlying probability space, and the values real valued means these can take both positive and negative values. Okay. Now to understand this equation, imagine any real number. Forget about mapping, we will understand about this real valued mapping slightly later, but think of any real number, positive or negative. Suppose 5, then you can write it as the difference of maximum of 5 and 0 minus maximum of minus 5 and 0, right? Because what is maximum of 5 and 0? That is 5. What is maximum of minus 5 and 0? That is 0. So any positive real number can be written as x equal to minus of x equal to maximum of x0 minus maximum of minus x0, because when x is positive, this part will be equal to x and this part will be equal to 0. Similarly, when x is negative, this part, the x plus, which is maximum of x0, that will be 0, but this minus of x will be positive, so the maximum will be minus x, and so minus x will be x. So for negative number also, if x is a negative number, then you can the x plus will be 0, but x minus will be minus x, so minus x will be x. So whether x is positive or negative value, this equation will be always true. So now we can define the same thing for any real valued function. Why? Because for real valued function means what? For every point in the domain, xw is a real number. So we are applying that same logic that we have discussed pointwise. So any real valued function can be expressed as the difference of two non-negative valued function, namely x plus and x minus. This you can think of the positive part of x, and this you can think the minus of the negative part of x. So these are two non-negative valued functions, and this is a matter of simple exercise to verify that if x is a random variable, that is satisfying the definition condition in the definition, then maximum of x0 and maximum of minus x0, they are also random variable on the same space. So any real valued random variable can be expressed as the difference between two non-negative valued random variables on the same space. This is the most important concept. Now what we will do is that define expectation of x equal to expectation of x plus minus expectation of x minus. Why? Because you see that so far we know how to define expectations of non-negative valued random variable. So you see, this is a stage by stage development. First we have defined expectation of simple random variable, then we have used to define expectation of non-negative valued random variable, then we have proved some properties, developed MCT, and then we have gone on to gotten a second definition of expectation of a non-negative random variable, and now we are using the definitions of expectation of non-negative valued random variable to define expectation of x. Now prima facie this is all good, but there is a slight problem. You remember that for any non-negative valued random variable, expectation may or may not be finite. Now what happens if both of them are not finite? Because you are defining as difference, so then you will get an infinity minus infinity condition. Now in mathematics, infinity minus infinity is not defined, so this situation is to be avoided at all costs. If it so happens that expectation of x plus and expectation of x minus both are not finite, then for such a real valued random variable x, we say that the expectation does not exist. So this is an important distinction from all the previous cases. So for any simple random variable, expectation is always a finite real number, right? Because it is a finite sum of real numbers into corresponding probabilities. For non-negative valued random variables, it is defined as a supremum over a non-negative set of numbers. So that supremum is either finite or infinite, but this concept is always defined. You can always take talk about supremum of a non-negative set of numbers. There is no issue, there is no problem like undefinedness here. And so you have a non-negative random variable, its expectation is well defined, it may or may not be finite. But when you come to expectation of a real valued random variable, you have a peculiar situation where you can have a infinity minus infinity situation. So in that case, we say expectation does not exist. This is different from expectation not being finite. So this has to be borne in mind. So for real valued random variable, there are examples of real valued random variables for which expectation does not even exist. So for them, we are not saying that the expectation is not finite. The concept of expectation is not defined. So this is the first major distinction. So one example is that we will see that when x follows Cauchy distribution, this is what is happening. But anyhow, so when we talk about expectation of non-negative valued random variables, real valued random variables, we have to assume, so this is the condition that I have stated, at least one of them has to be finite. Now suppose one is infinite, other is finite, so then it will be infinity minus a real number, so that is infinity. There is no problem. That is not finite but still exists. So if the expectation of, here there is a typo, it should be x minus, okay. So if this is infinite but this is finite, so this is a real number minus infinity, so this is minus infinity. Again, this is a concept that is well defined. There is no issue with it. So the expectation of x need not be a finite real number. It may be plus infinity or minus infinity when any one of this is not finite. So if however both of them are finite, then expectation of x is the difference of two real numbers, so it is a real number. So we will talk about random variables with finite mean, or L1 random variables. So that would refer to the situation when both of these are finite, okay. But as of now, we are defining expectation for those random variables for which at least x plus or x minus has a finite mean. So here is or, and the correction should be here you should have a minus. So now you see, one important food for thought at this stage is that I have said that any x is difference of x plus and x minus. What happens when I add x plus and x minus? So x plus is also non-negative valued, x minus is also non-negative valued. So is it clear why x minus is non-negative valued? Because you are taking the maximum of minus of x and 0, so it can never be negative, right? Even if this quantity is negative, it will be 0, and if x is negative, minus x will be positive, so that will be the positive number. So X plus and x minus, when you add them, they give you a non-negative random variable, right? And what is this sum? This sum happens to be absolute mode of x. I am sure you all know what is mode of x. For any number, think of a number first, always, when you think about a concept first. So what is mode of any number? It is the x when x is positive, and it is minus x when x is negative. So you see that this is what you will get. So if x is positive, then x plus is x and x minus is 0, and when x is negative, then x plus is 0 and x minus is minus x. So that is what exactly you get. So this sum is expectation of mode x. So now I will bring an important concept of mode x, that for any real valued random variable you look at mode of x. So how will you define mode of x? It is another random variable. How it is defined? Mode of x w will be equal to mode of xw. So it is just like you define a function, just like you define the absolute function pointwise. So you have any real valued function f. What is mode of f? So it will be defined pointwise as a modulus of fw at every point in the domain. So this is a non-negative valued random variable. And now what is this? Now from the last lecture, you know, expectation of the sum of non-negative valued random variable is the sum of their expectation. So expectation of mode x will be equal to expectation of x minus plus expectation of x minus. So I might write here. So what I am saying is, this is a very important concept, so we should spend some time. Expectation of x mode x equal to expectation of x plus expectation of minus. So these are expectations of non-negative valued random variables that we all know. So you see the difference in the two. This is something we are getting from the properties of non-negative valued random variables and that its expectation that we have discussed, and this is the definition. So this we have gotten from the properties of expectation for non-negative random variable, but this equal to but this is not a property. This we have not proved. We cannot prove this. This is our definition provided one of them is finite. Otherwise it is not even defined. So you have to remember expectation of x is the difference provided one of them is finite, and otherwise this is not defined. And but for any real valued random variable, expectation of mode x is always defined, and we get this equation from what we know so far. So now an important relation between what is the relation between these two? This is the difference between two non-negative real numbers. When I say non-negative real numbers, I am assuming both are finite, and this is the sum of the two non-negative real numbers. So obviously